In section 15.2, we're looking at line integrals. Our objectives are to understand and use the concept of a piecewise smooth curve, write and evaluate a line integral, write and evaluate a line integral of a vector field, and write and evaluate a line integral in differential form. In this example, we want to find a piecewise smooth parametrization of the graph of C shown in figure 15.7. This path is beginning here at the point 0, 0, 0 and moving along the first path C1 to the point 0, 2, 0, moving from there along the path C2 to the point 1, 2, 0, and then moving from there on the path C3 to the point 1, 2, 1. Now there are many ways of coming up with parametrizations for the path. I'm going to present you with one method here. Because C consists of these three line segments, C1, C2, and C3, you can construct a smooth parametrization for each segment and piece them together by making the last t value in Ci correspond to the first t value in Ci plus 1, as follows. For example, C sub 1, if you notice that your path is going from the point 0, 0, 0 to the point 0, 2, 0, the x is a constant 0, the y is going from 0 to 2, and the z is going from 0 to 0. So our x is equal to 0, and z is also equal to 0. And the parametrization for y, we can say y is equal to 2t. And the time interval is from 0 to 1. You can check the location along this path by plugging in the endpoints of the time interval. For t equals 0, you get the coordinates 0, 0, 0. So that's your beginning location. And at the time equals 0 at the beginning of the time interval. At time equals 1, if you plug in 1 for t, you get the point 0, 2, 0. So along that path, the time interval is going from 0 to 1. From the point 0, 0, 0 to the point 0, 2, 0. Now our next C2, the time interval is going to begin at 1. Now the parametrization for that path is as follows. The x at the beginning is 0, and it's going to x equals 1. The y is starting at 2 and it's staying at 2. The z is starting at 0 and ending at 0. So the y and z are constants. Y equals 2 and z equals 0. Now the way we come up with this parametrization is that t equals 1. The beginning of that time interval, the location for x is equal to 0. At t equals 2, the location for x is equal to 1. So we're able to begin at the location 0 and move to the location 1 in that given time interval. And then for the last portion of the path, we're moving from the point 1, 2, 0 up to the point 1, 2, 1. The x and the y are constant. X is equal to 1 and y is equal to 2. But the z is moving from 0 up to 1. And the parametrization for that is t minus 2 for the time interval from 2 to 3. If you plug in that t equals 2, you'll see that the starting z for that piece of the path is 0, and then up to t equals 3, plug in 3 for t, and you get the ending location is 1. So that is an example of a parametrization. We've got 3 different paths. We're going to put them all together to come up with the vector valued function r in terms of t is equal to each of those. We're going to set the x, the y, and the z to be equal to the components of the vector valued function, and we've broken this up into different time intervals. Now because each of those paths, C1, C2, and C3 are smooth, we say that the entire path from the start to the finish is a piecewise smooth parametrization. And the parametrization of a curve induces an orientation to the curve. So if you look back at the picture, you'll see that the arrows would indicate the orientation. In this example, we want to find a parametrization from the point 0, 0 to the point 2, 4 along the curve y is equal to x squared. This is a path in the plane, so our parametrization is going to have an I and a j component. You can try this one on your own, pause the video, and then come back and check your work. I'm going to begin by sketching the path. Start in 2 dimensions in the plane, starting at the point 0, 0, and then moving to the point 2, 4. But in this case, it's not a straight path. We're moving along the curve y is equal to x squared. So the path is going in that direction. We indicate the orientation of the path by that little arrow. So here again, the beginning point is 0, 0. The ending point is 2, 4. And this path here is along the path y is equal to x squared. Now there are many ways of coming up with a parametrization for the path, so it's not unique. One thing you can do is, you know, the x is changing, and we can let the x equal t. So as t increases, this x is going to increase. And then if you're using the equation y is equal to x squared, then you already know you've set x to equal t, then you can say y has to equal t squared. So the parametrization is going to be r of t. Notice we're now switching to the notation for a vector valued function, is going to equal your x of t I plus your y of t j. And we can then write this as our r of t for this path. Since our x of t is equal to t, it's going to be ti plus y of t is our t squared j. And with any parametrization for a path, you do want to also give a time interval. And in this case, if we plug in t equals 0, the location, if t is equal to 0, the location using these parametrizations would be x is equal to 0 and y is equal to 0. So you would be right here at the point 0, 0. At our ending point, at t is equal to the value that would bring the location of x to equal 2, then our t would have to equal 2. And if you plug it into the parametrizations, you get x is equal to 2, and then y would equal to 2 squared, or 4. So the time interval for this parametrization is for the time interval from 0 to 2. Okay, this is our parametrization for the path. Again, this is not unique, meaning there are many, many ways of finding parametrization that would result in the same path. The difference would be have to be adjusted in your time interval and how you define your parameters. All right, for this next example, we want to find a parametrization for the straight path from the point 1, 4 to the point 5, 2. So I'll begin with a quick sketch, beginning at the point 1, 4 and ending at the point 5, 2. We're going on the straight path and indicate the orientation. And there are many ways of doing this. One is by coming up with the equation of the line that goes through those 2 points, finding the slope and the y-intercept, and then you would define your x and your y. Let's go ahead and do that, and then I'll show you an alternate way of finding a parametrization. Well, you know the equation of a line. If you know a point and you know a slope, you can find the equation of a line using the form y minus y sub 1 equals the slope times the quantity x minus x sub 1. Well, we have a point. We can use either one of these points. We can use the point 1, 4, but we also need to find the slope. So you can find the slope between these 2 points. Remember that the slope is the rise over the run. You can use the slope formula. In this case, we're moving down 2 units and then over 1, 2, 3, 4 units. So we can say the slope of this line here would be 2 minus 4 is negative 2, 5 minus 1 is 4, or negative 1/2. So if we use a 0.14 and a slope of negative 1/2 and plug it into the equation of this line, we can then come up with a parametrization for the path using a vector valued function. By plugging it in, we get y minus our y sub 1 of 4 equals negative 1/2 x minus our x sub 1 of 1. If we solve this for y by distributing, we get y minus 4 equals a negative 1/2 x plus 1/2. And then by adding 4 to both sides, we get y equals negative 1/2 x, and then 1/2 plus 4 would, negative 1/2 plus 4 would be 4.5, or if we write that as a fraction, 9/2. So this is actually the equation of the line that goes through those 2 points. Y equals negative 1/2 x plus 9/2. So when we come up with a parametrization, we can say let x equal, we're going to introduce that parameter t, and we're going to let y equal the negative 1/2 t plus 9/2. So here's your x equals and your y equals. So the parametrization can then be written as r of t, using that vector valued function notation, is equal to your x sub ti plus your y of tj, and you can plug in what you're setting x is equal to t. So it would be ti plus all of this negative 1/2 t plus 9/2 j. And then with every parametrization for a path, you do need a start time and an end time. So let's determine the time where you start. In this case, when x equals t, then our start time, t, would equal 1. So our start time here, t is equal to 1, would bring you to the start, and then t is equal to 5 would be your end time. So the time interval would be from 1 to 5. And you can check to see if this parametrization gives you your start and your end point by plugging in t equals 1, and you get the location 1i plus 4j. When you simplify it, that will give you the first location. And then when you plug in the ending point, when t is equal to 5, you get 5i plus 2j. So it will give you the same start and the end time. Okay, this is one approach. However, I would suggest an alternate approach. And this will actually work for all straight paths, whether in the plane or in space. Okay, so are you ready for a shortcut? This is my suggestion for any time you have a straight path. You can use the following model equation. X is equal to x sub 0, that's the starting x, plus a times the quantity t minus t sub 0. And then you can use y equals y sub 0 plus b times t minus t sub 0. Now I've introduced some variables here. X sub 0, y sub 0, that's going to be your initial, that's going to be your start point. X sub 0, y sub 0, that's going to be your starting point. Now the components a and b, that's going to be your vector from your start to your end point. From a to b, or your change. A is going to be your change in your x, how the x changes from the start to finish, and then your b is going to be your change in your y. And then t sub 0 would be your start time. So if we let our t sub 0 equals 0, starting at t equals 0, and then your starting point is, you let your x sub 0 equal 1 and your y sub 0 equal 4. That's your starting point. And then you let your a equal how your x is changing. Your x is starting at 1 and ending at 5. So the a is going to increase by the x is going to increase by 4, so a is going to equal a positive 4. And then your b is how the y is changing. The y starting at 4 and ending at 2 is changing by a negative 2. So your parametrization can then be written as x equals your starting x of 1 plus how the x is changing from 1 to 5, it's changing by a positive 4 amount, times the quantity t minus t sub 0. We're using a t equals 0 as your start time. So that's going to be your x equals, and then your y is equal to your starting y of 4 plus how the y is changing from the start to the finish. It's changing by a negative 2, t minus t sub 0, and our start time is 0. When we simplify this, we get x equals 1 plus 4t, and when you simplify this, you get y equals 4 minus 2t. So this is going to be your parametrization. Write it as a vector valued function, r of t is equal to your x of ti, it's going to be 1 plus 4ti plus your y sub t, y of t, j, that's going to be 4 minus 2t, j. And then when you use this technique, the time interval is always one change of time beginning at your t sub 0. So your t interval is going from 0 to 1. It's always going to be one change in time, a unit of time.